So here we've got the general form of linear second order constant coefficient homogeneous differential equation. So the only difference between any of them is a different number for A, a different number for B, a different number for C. What we do then is you get the eigenvalues. So you propose a solution of a constant times e to the lambda t, and you'll get the auxiliary equation of A instead of prime, you're going to get lambda squared. Instead of 1 prime, you're going to get lambda. And instead of no prime, you're going to get no lambda. So differential equation, auxiliary equation, the eigenvalues are the lambda. Some people call them the roots of the auxiliary equation, roots of the characteristic equation. And there's sort of three general cases. So let's look at some examples. The first example here, I've got the first eigenvalue, lambda 1, is 2, and the second eigenvalue is minus 7. So what does our solution look like? Well, the eigenvalues are real and different. So we know that we expect to get a solution, a homogeneous solution of the form some constant e to the first eigenvalue t plus some constant e to the second eigenvalue t. Now, these constants can be different. And how do we get those constants? The initial conditions. So the initial conditions have to do with the constants, the e to the lambda 1t and e to the lambda 2t. Those pieces have to do with the differential equation, have to do with the eigenvalues. So if I get real and different, here's the form of the solution. Now, I don't have any initial conditions, so I don't know how this equation starts, but I do know how it ends. As t goes to infinity, this e to the minus 7t piece goes to 0 no matter what this constant is. And this c1 e to the 2t goes off to, well, infinity if c1 is positive, or negative infinity if c1 is negative. So I end up getting then, I don't know what happens here, but I know eventually the solution like shoots off to infinity, or the solution shoots off to negative infinity. And I know that actually, I knew that as soon as I got an eigenvalue that was positive. Then I knew that the solution to that homogeneous differential equation, the homogeneous solution, was unbounded, shot off to positive infinity or shot off to negative infinity. Here's another example, but in this case, lambda 1 is minus 7, lambda 2 is minus 7. Basically what we see is two real and the same eigenvalues. So the structure starts out being the same for the general solution, some constant e to the first eigenvalue t, some constant e to the second eigenvalue t, except because they're the same eigenvalue, because the eigenvalues are identical, real and the same, you have to throw that extra t in front of the second piece. Now both eigenvalues are negative. So if I want to think about what happens to the eventual solution, again, I don't know how it starts. We're not given any initial conditions, so I don't know what the c's are, but I know eventually the solution approaches 0 because e to the minus 7 approaches 0 and t e to the minus 7 approaches 0. Now you might say the t goes to infinity, well, infinity times 0, yeah, but think of it as this. T over e to the minus, so they both go to infinity, infinity over infinity. You say something L'Hopital's rule, and you get this, which goes to a number divided by infinity, which is 0. So both pieces approach 0. So if both eigenvalues are real and the same and negative, the solution goes to 0. Last example here is, well, the last example has a complex conjugate pair of eigenvalues. So we've got minus 3 plus or minus 4i. Now in this case, writing down the general solution, I can't just go e to the first eigenvalue t, e to the second eigenvalue t. When you see complex conjugate eigenvalues, you know you're going to get trig in the answer. So the homogeneous solution could be equal to c1, again I'm going to have two constants because it's a second order equation, e to the real part of the eigenvalue t times cosine imaginary part of the eigenvalue t plus the other constant e to the real part of the eigenvalue t times sine imaginary part of the eigenvalue t. So the real part of the eigenvalue goes with the exponential. The imaginary part of the eigenvalue, the 4, goes in the trig, cos and sine. Now I've written it as two different pieces here, a cos piece plus a sine piece. You could also write it as a e to the real part t sine, but I'm gonna copy paste this here. That a is one constant. I need another constant because we have a second order equation. The other constant goes in here. It should be like plus phi. So here I've got two constants, C1 and C2, in the version where I write it as a cos plus a sine, or when I write it as one shifted sign, I still have two constants, the a and the phi. How do I find the a and the phi? Those two constants, initial conditions. How do I find the C1 and C2? Initial conditions. Anyway, now we've got the general form of the solution. We didn't really need that to sketch the graph, though. We didn't really need the general form of the solution to talk about the eventual state of the solution. So let's take a look here. Because the real part is negative, this e to the minus 3t, that's going to go to 0. This e to the minus 3t, that's going to go to 0. Or if I'm looking at it in the other form, that e to the minus 3t they're all going to go to 0. So eventually the solution approaches 0. But there's trig involved, so we're going to have some oscillation. I don't know how it starts, so I don't know when t is equal to 0 what y is. But I do know that it's going to oscillate down to 0. It's going to approach 0. And I even know more than that. Because the imaginary part is 4, the period is going to be 2 pi divided by the imaginary part. So in our case, pi over 2. Pi over 2 is going to be the distance between, well, it's going to be the period. So the distance between intercepts, the distance between peaks, the distance between troughs, whatever. So I can make a pretty good sketch. So let's go back. So when you have complex conjugate eigenvalues, you can see if the real part is negative, then the solution oscillates down to 0. If the real part would be positive, if that was plus 3 instead, then it would have oscillated off to infinity, getting bigger and bigger, but the period would still be the pi over 2. So if the real part is negative, then the solution goes to 0. If the real part is positive, then the solution oscillates off to infinity. So that we can make that let's make that a rule. If the real part of both eigenvalues are negative, then the homogeneous solution goes to 0. Else, the homogeneous solution goes to plus or minus infinity, that's an h, becomes unbounded, doesn't exist, that kind of thing. So this rule works for if they're real and different, they both have to be negative for it to go to 0. If they're real and the same, then they're both the same, and if they're both negative, it goes to 0. If they're both the same and positive, goes to infinity. And it works for complex conjugate because we're asking for the real part of the eigenvalue.